Welcome back. What I would like to do now is go over a couple of examples of Bode plots. In particular, these Bode plots will have, the first one is a 0 at the origin and the second one has a pole at the origin, and I also have poles and zeros occurring before omega equal 1, which is not the origin, but it is a frequency where a lot of times we locate the pole or zero at the origin. Its magnitude is, we say, oh, it's going through 0 dB at omega equal 1. But the pole and zero at the origin is always acting. If it's a 0, it's always going up with a slope of plus 20 dB per decade, and if it's a pole, its slope, it never breaks, is always going down at minus 20 dB per decade. But both of those actually by themselves pass through 0 dB at omega equal 1. Let's start with this first transfer function, g sub 1 of s, sketching its Bode plot. The very first thing that we need to do is put the transfer function into time constant form. This allows us then to normalize the constant coefficient, and that allows us not to have to worry about what the magnitude is doing prior to when it breaks. It will be contributing 0 dBs unless it's a pole or 0 at the origin. In this case, in the first one, let me go back and see what I had just to get started. The 10 remains factored out upstairs, and then we have to factor out the two constants or pole locations in the denominator. We have 10 times s, that's the 0 at the origin. Then we have the 0.1 factored out of the first term, and then we have the pole at 10, its factored form in time constant form. The 0.1 and the 10 in the denominator conveniently cancel, and we are left then with two poles in the denominator, one at 0.1 and the other one at 10. Now what we want to do is look at the easiest way, I think, to sketch Bode plots when you're first learning is to go ahead and just look at all of the individual terms, sketch their contributions in magnitude and phase, and then at the very end just go ahead and add all of those up. Because we're dealing with magnitudes in dB, we can simply add each individual component's contribution. Let's then start with the easy, or the gain. Then we will try to progress from lowest frequency up to highest frequency, and we'll actually treat the poles and zeros as if they were something magic happening at omega equal 1, but that's only because we can now, that gives us a nice place to locate that sloping line through going through 0 dB at omega equal 1. Again, whether it's up or down depends on whether it's in a 0 in the numerator or up, and it's down if it's in the denominator or if it's a pole at the origin. Let's now look at the gain piece. Here we have a gain of 10 in this g sub 1 of s, which says that our magnitude is simply going to be 20 times the log of that. That's a convenient value. Log of 10 is 1, or we now have the gain contributing 20 dB, and that occurs for all frequencies omega. Our phase, since this is a positive number and not negative, is going to be 0 degrees, and again that too, since it's not a function of frequency, it contributes 0 degrees for all omega. Again, going from smallest to largest, if we look at our pole at s equal minus 0.1, let's look at its magnitude. Because we've now put it into time constant form, that particular pole factor will be 0 dB until we reach the break frequency, which is actually the value of the pole, and so it's going to be 0 dB until it breaks at omega equals 0.1, and that's in radians per second. After that fact, or after the break, it then has a slope for all remaining frequencies of going down, since it's a pole, of minus 20 dB per decade thereafter, or after omega equals 0.1. The phase, we have to worry a little bit more about the phase because its slope begins and then it quits and stops sloping. The magnitudes in both poles and zero factors, once they break, they never stop contributing a slope. The phase is a little different. It kicks in, and in this case the phase kicks in, starts to make some contribution a decade before the break frequency. It continues to make contributions until a decade after the break. The way I'm going to phrase that is I'm going to say that the pole at s equal minus 0.1 has 0 degrees phase until we get to a decade before 0.1, which is 0.1 times 0.1, or 0.01, or 10 to the minus 2. I've conveniently selected these frequencies. Right at the break frequency, because it's a pole and it's just a single factor, it will be equal to minus 45 degrees. So now we're sloping at 45 degrees per decade, and it's going to be that slope at the break, omega equal minus, or 0.1. Then it will reach minus 90 degrees a decade after, and at that point it stops sloping, but it continues to contribute 90 degrees after a decade beyond the break, and I'll say that it's going to be minus 90 degrees after omega equal 10 times 0.1, or after 1 radian per second. Then we have to worry about, in this particular transfer function, we had a 0 at the origin. As I said before, with respect to the magnitudes of these singularities at the origin, the magnitude, there is no break. Or we could say it's always on, it's always acting, it's always sloping, and the magnitude is sloping. Since it's a 0, which is upstairs, it's going to be sloping with a positive 20 dB per decade. And what we will do is this magnitude curve, well, so it's sloping at 20 dB per decade, and the curve passes through. This is how we can locate that sloping line. It's going to pass through 0 dB at omega equal 1 radian per second. Again, it's always sloping, it's going up, so below omega equal 1 it's below 0 dB, and after omega equal 1 it's above 0 dB, but it's always sloping at plus 20 dB per decade. Its phase, like its magnitude, never changes, but it actually, because it's upstairs and it's a 0, it's going to give us 90 degrees for all frequencies, and that 90 degrees never changes because it is located at the origin. We only have one more factor to look at, and that's the pole at omega equal 10, or maybe I should say, since I'm calling these poles, let me say that that's a pole at s equal to minus 10. The magnitude here is going to be 0 dB. Since it's in time constant form, we've already normalized the value of the pole out, and it's going to remain 0 dB until it breaks. It will break right at the pole, which is 10 radians per second. Because it's in radians, and it's going to have a slope, since it's downstairs in a pole, of minus 20 dB per decade for all frequencies or thereafter beyond omega equal 10. The magnitude, again, once it begins sloping, it never stops sloping. The phase of these pole and zero factors is a different story. It turns on and turns off. It's going to be contributing 0 degrees until we reach a decade before the break. In this case, a decade before 10 is just 1, or 0.1 times 10, which is 1. It will be, because it's downstairs, minus 45 degrees right at the break. This is then on the sloping line. It will slope again, or continue to slope at minus 45 degrees per decade until it reaches a decade beyond the break, which in this case is 10 times 10, or 100. And at that point, it remains minus 90 degrees from that point onward. Let's now see if we can sort of roughly sketch that with this by hand. And to sketch this, what you really want to do is go back to either the pole zero form of the transfer function or the time constant form, and look at where your smallest frequency is and your largest frequency. In this case, our smallest frequency is 0.1. It'd be nice to go a decade before that, because that's where the phase kicks in. And our highest frequency is 10. We go a decade after that. So our Bode plot really is going to range in terms of our frequency at 10 to the minus 1 times 0.1, or 10 to the minus 2 up to a decade beyond 10, which is 10 times 10, or 100. So we now have 4 different decades to worry about in this particular Bode plot, from 10 to the minus 2 and all the way out to 10 to the plus 2. So now there's 10 to the minus 2. This will be my magnitude plot. 10 to the minus 1, 10 to the 0, 10 to the 1, and 10 to the 2. And I will try to then quickly identify somewhat underneath those. Ideally, they would be exactly in line. This will now be my phase plot. And what I want to do, I'll try to do this with a slightly thinner line. Let me now introduce my different pieces. I had my gain piece, which was 20 dB for all frequencies. Let me just say this is now going to be my 20 dB level. That's due to the gain. Then I had a pole at 0.1, which is right here. It's going to kick on right at the break, and it's going to then go down 20 dB per decade after that. So let me dash that one in. That's my pole at 0.1. I had a 0 at the origin. That's going to pass through 0 dB at omega equal 1. It will be down at minus 20. Whoops, I need to sort of be consistent with my values that I'm using. And then it's, well, my slopes probably won't be very accurate, but then there's beyond 1, omega equal 1, and then there's beyond 10. That now is my magnitude contribution due to my 0 at the origin. And finally, I have a pole at omega equal 10, and it will then be going down at 20 dB per decade after that. Those are my individual contributions. Now I simply need to add those up. What I need to remember, though, is I have something that's always active, which is this 0 at the origin. It's always on. It's now at minus 40 at 0.01, but I also have 20 dB that's always active from the constant. The net result of that, minus 40 plus 20, is minus 20, and that's really where I could start my curve. It's now going to be coming up at 20 dB per decade. I'm basically adding 20 dB to this 0 contribution line, it's going to then go up to my first time that I entertain a break, which is my pole at point 1. At this point I have a pole, one pole acting, which gives me a slope of minus 20. I have a 1, 0 sloping at plus 20. The net slope is 0, and so now I just keep going at 0 dB until I reach my next break. My next break doesn't occur until I reach my last pole, which was at 10, and then I simply follow that down, and the red now indicates my magnitude plot for G sub 1 in dB. Let's now try the phase. The phase, we have to worry about where they start and where they stop. In this case, the gain contributed 0 degrees. We really don't have to worry about that. We had a pole at point 1, and what I'm going to do then is I'm going to say at a decade before point 1, the pole is going to want to give me something that goes down, and then it will turn off a decade after, and that's how I'm going to maybe indicate to myself my little bookkeeping that I need to keep track of. I now can say that I'm going to be going down to minus 90, and I'm going to be going through 45, minus 45 right at the break, and then I will be continuing on after that at minus 90. I have my 0 at the origin, which is always plus 90. Maybe in this case, since I'm going to sketch these components individually, let me go ahead and just not keep track of my starting and stopping, and I can just do it. This will now be plus 90. I may not be consistent. This was minus 90, this was plus 90. Then I have one more pole at omega equal 10, so that's the break, but it starts a decade before that and ends a decade after, and it now contributes 90 degrees over those 2 decades. What I now will do is combine all of those. The 0 at the origin is always on, and the only thing happening then at low frequencies is a plus 90. At 0.01, the phase of my first pole starts sloping the phase curve, and I get down to minus 45 from it, but I already have plus 90 from the 0, so I'm actually at a net plus 45. I now am plus 45, but I'm still sloping at 45 degrees per decade, and I will then get to 0 degrees right at 1. The pole at 0.1 turns off, but now the pole at 10 turns in terms of contributing, and consequently my slope shouldn't be changing, and I end up then stopping the slope at 100 and continuing at minus 90 degrees beyond 100, and that should be consistent with our Bode plot, or with our transfer function. We had a 0 at the origin. Our phase then starts at plus 90. We had 2 poles and 1 0. We had a pole 0 excess of 1, which means at high frequencies we should be sloping, or I'm sorry, we should have an angle of minus 90 degrees. Our magnitude plot, because of the pole 0 excess, we have 2 poles, 1 0. At high frequencies, 2 minus 1 will have effectively 1 pole active, and our slope for high frequencies should be minus 20 dB per decade on the magnitude plot. At low frequencies, our slope, because of the 0 at the origin, should be plus 20 dB per decade, and that, in this case, low frequencies is something below 0.01. And in between, we're actually flat in magnitude between 0.1 and 10, and in the phase we're sloping at minus 45 degrees per decade from 0.01 all the way up to 100. That's our first example. Let's now look at the second transfer function, which was G sub 2 of S. We now need to get that in time constant form, or we factor out then our poles and zeros to obtain a constant of 1 in those factors. We had a pole at the origin. we had a pole at 0.01, and we had a pole at 100. And I've conveniently selected those two factors to allow that to cancel, and we're left then with a transfer function in time constant form of 0.5 s over 0.5 s over 0.1 and then we have our pole at the origin, a pole at 0.1, and another pole at 100. And if we work through this like we did before, we'll just talk our way through this particular example, and hopefully that will start to make sense. Let's start with our gain. Now that we're in time constant form, we can just treat each of these factors individually. We have our gain of 0.5. So in this case, the magnitude plot, or the magnitude of our gain, is going to be 20 log of 0.5, and we could get out our calculator, or we could start to say, well, let me see if I really understand what's going on. That's actually just 5 times 0.1, or that's 20 times the log of 5 plus the log of 0.1. Maybe you know your logarithms for all of these integers between 1 and 10. Maybe you don't, but you can always just use your calculator. In this case, that's minus 1. The log of 5 is about 0.7. It's 0.699, so we'll say that's about 0.7, or the overall impact here is minus 0.3, so that we now have 20 times minus 0.3, or minus 6 dB is what the gain of 1/2 contributes. And maybe you would have remembered that if you remembered that 3 dB down corresponds to the half power point, which in magnitude is 1 over the square root of 1 over the square root of 2, which is 0.707. That's the magnitude for all omega. And our phase, since the gain was a positive gain, it's 0 degrees, again for all frequencies omega. Now let's move again from lowest frequency to higher frequency. Our first singularity was this pole at minus 0.01. It has a magnitude, so I hope now you're seeing that this is actually, you can just number crunch, or just sort of step through this process, and then at the end add everything together, and it's not that hard to put these Bode plots, build them up. So now our magnitude is 0 dB until we reach our break, which is 0.1 radians per second. After that, our magnitude now slopes at 20 dB per decade. Since it's a pole, it's going down, and it never stops sloping once it starts. It's a pole factor with a non-zero value. The phase, again, the phases start a decade before and stop sloping a decade after. In this case, we're going to be 0 degrees until a decade before our break frequency, which is 0.1 times 0.01, or 0.001. Let me write that in terms of powers of 10. It's a pole. Our phase is then going down, and it will be at minus 45 degrees right at the break, which is 0.01, and then it will be at minus 90 degrees and stay at minus 90 degree after a decade beyond the break, which is 10 times 0.01, or 10 to the minus 1 radians per second. Moving then to the next higher frequency, we have a 0 at s equal minus 0.1, In this case, our magnitude, again, because it's in time constant form, is 0 dB until we reach our break. Our break frequency is at 0.1. Because it's a 0, it's going to be a numerator factor, which is upstairs, so our slope is now plus 20 dB per decade after it breaks, and we've just identified where it breaks, which is 0.1 radians per second. We'll be sloping at plus 20 dB per decade thereafter. The phase, again, in time constant form, it's going to be 0 until a decade before the break, which is 0.1 times 0.1, or 10 to the minus 2 radians per second. It's a 0, which is upstairs, which says that it's going to now be halfway to its destination of plus 90 degrees right at the break, so it'll be at 45 degrees right at the break of omega equals 0.1. It will then reach plus 90 degrees a decade after the break, and thereafter it will be locked at plus 90 degrees at 10 to the 0 or at 1. The next singularity that we will examine then is this pole at the origin. What you have to remember, though, is this guy never breaks. He's always on. Even though we're treating him as a sort of a frequency that's bigger than 0.1, it's just because omega equal 1 gives us a nice location with which to pin down the magnitude. In this case, we have a pole at the origin. It's downstairs. The slope then is always negative. And in this case, again, because we're treating these pieces, components, individually, it's going to be passing through 0 dB right at omega equal 1 radian per second. The phase of this particular factor, which is a pole at the origin, never changes. It's downstairs. It's going to always be contributing 90 degrees for all frequencies. Then we have our last pole as we move to higher frequencies at s equal minus 100 radians per second. Its magnitude is going to be 0 dB until we reach the break. It's going to break right at 100 radians per second. After that, it will be sloping. Since it's a pole, it's downstairs, it's going to be sloping minus 20 dB per decade thereafter. And we really don't have to worry about turning it off. It's a pole, and its magnitude, once it kicks in or breaks, it never shuts down in terms of its slope. Its phase is different. Its phase kicks in a decade before its break, which is 0.1 times 100, or right at 10. It's downstairs or a pole. It's going to be going down in its slope. When it is sloping, it slopes over 2 decades. It will be right at the midpoint of minus 45 degrees, right at the break frequency. It will then reach its destination of minus 90 degrees. Again, these are straight line plots at a decade beyond the break, which then gets us up to 1,000 radians per second, where it's now minus 90 degrees. If you're keeping track of our frequency interval, you'll see that the highest frequency that we need to worry about is 1,000. And if we go back to where we started, we will see that in our very first singularity, which was a pole at 0.01, we need to start or worry about things happening a decade before that, and at that point it's 10 to the minus 3. So now we're looking at a frequency interval or range quite large. We're now letting omega live between 10 to the minus 3 and 10 to the 3. I'll try to squeeze that in to my Bode plot, but that tells you then how we need to spread out our intervals on this Bode plot. And as I've said before, ideally these are all lined up. I'm doing this fairly quickly, but I think you get the idea. You could spend a little bit more time, but really what we're doing is we could think of doing this on a napkin, and now we're just trying to sketch this out so that if we do it in MATLAB, we'll actually be able to verify whether or not we entered the information correctly so that MATLAB's giving us the right answer. Remember what we had for our magnitude. That's now what we're going to plot here in dB. We started with a gain, and that gain was minus 6 dB. Again, let me try to do that in a little finer. Let me say that this, well, I don't know, let's say that's 20 and this is minus 20 and that's plus 20. So now let's just say that this represents minus 6. That's due to our gain. The next thing we need to worry about is a pole at 0.01, which is right there, and we said we'll go down 20 dB per decade thereafter. So you can see that I'm going to be going quite far if I continue that, but it would continue indefinitely. I may not make it go any further because I'm going to be into my phase plot. I now have a 0 at 0.1, so it's going to be going up at 20 dB per decade. I have a pole at the origin which never breaks. It's always on. It's going to go through 0 dB at omega equal 1. It's going to then be going through minus 20, minus 40. It'll be plus 20, plus 40. Well, that's pretty poorly drawn, but that's actually a straight line. I now have a pole at minus 100, which is over here, and it's now going to be at minus 20 at 1,000, and it continues. Now what I want to do is actually add all of those pieces together, and I begin with my piece that's well, this is not giving me enough room, is it? So at minus, or 10 to the minus 2, or 0.01, my pole at the origin should be giving me 40 dB. So let me change that slope a little bit. It should be 40 dB above 0. This one was being a little bit too aggressive, I think, with the slope at that point. Going to have to be more patient. And it's going to be 60 dB at 0.001. So if I can sort of draw that, that's now my pole at the origin magnitude. I can come down 6 dB from that everywhere because that's what this guy's saying, and if I come down 6 dB from that, I will now be at 6 dB down from plus 40 is minus, or is 34 dB. Now I start kicking in my first pole, and let me go beyond that. I should be, at this point, I'm minus 20 due to my pole at 0.01, and I'm plus 20 due to my pole at the origin, and I'm minus 6 due to the gain. So I should now be at minus 6. My slope is now changing, where I'm now going down at 40 dB per decade beyond 0.01. At this point, though, I now have 20 dB down for the pole at the origin, 20 dB down for the pole at 0.01, and plus 20 dB up for the pole, the 0 at 0.1. So now I need to go down 20 dB per decade, and that now says that I should be, if I was at -6, I should be at -26, -46, and then -66 at 100. And now my slope is 20 dB per decade, so this is now -20 dB per decade. This is -40 dB per decade, and this is -20 dB per decade. And finally, I now am sloping more. I was at -66, if I remember right. Now I need to go down 40 dB from that point, so I should be at -106 dB down, and my slope now is -40 dB per decade. Obviously, you can be a little bit more accurate when you're doing this in a more calm and relaxed environment. Let's now look at our phase. Our phase plot, the contribution due to our gain is 0, so we're not going to worry about that. We have a pole at 0.01, which starts contributing phase at 10 to the -3, and it will be all the way down to -90 a decade beyond its break. And we then have this contribution due to that first pole at 0.01. We then have a 0 at 0.1, or it's now going to begin contributing phase at 10 to the -2. It will stop contributing phase at 1, and so its phase contribution looks as sketched. Then we have our pole at the origin, which is always going to be giving us -90 degrees. Those will actually be on top of each other, but I'm illustrating the fact that there's two lines there by sort of showing those separated. And finally, we have a pole at 100, and so it kicks in at 10 and quits sloping at 1,000, and that's now its picture. We now should be at a point where we can start sketching these or adding these up. We now have -90 degrees is where we are starting. We then hit this pole at 0.001, and we go down at 45 degrees per decade until we reach our next break, which occurs due to the 0. The 0 is going up 45, this pole is going down at 45. Those slopes cancel until the pole slope stops. When it stops, now the 0 is the only thing that's changing as a function of frequency, and it's going up 45 degrees per decade. So now we come up and it turns off, so now we're flat. Then it kicks, the pole at 100 starts contributing phase at 10, and it goes down and contributes phase until we reach 1,000, and then it kicks off. So now let me just draw a straight line between -90 and -180, and that should be consistent with our phase curve. We're starting at -90 degrees. This is the phase of G sub 2. We're starting at -90 because we had a pole at the origin. We have, if we go back to our transfer function, we have 3 poles and 1 0, or a pole 0 excess of 2, meaning at high frequencies we better be at an angle phase of -180 degrees because we have 2 more poles than zeros. In our magnitude plot, because we have 2 more poles than we have zeros, or our pole 0 excess is 2, at high frequencies we better have a slope of -40 dB per decade. At low frequencies, because of the pole at the origin, we had a phase of minus 90 degrees, and we have a slope of minus 20 dB per decade. Hopefully those ideas, by sketching this, are more firmly clear in your own head, and that will help you better understand Bode plots, starting with the pole zero form of those expressions and working through the time, deriving the time constant form, and then sketching the Bode plots from those time constant forms. I hope that was helpful.